Hello, in this video we continue our study on antiderivatives. We solve some differential equations with initial conditions. Okay, so we know integrating or indefinite integrating means anti-differentiating or solving differential equations. So suppose that you have the following equation: y prime equal to f of x, right? Or we know the derivative of the function y. You want to recover the function y, so that is antiderivative of fx dx, right? And of course, in this case I would write plus c. So or you may write like this: y plus c equal to f of x dx, because we know, if y is antiderivative of the function f, then y plus c is also antiderivative. Okay, so the problem is we have a family, so we need to recover the function. Is that correct? Then we need to determine the c, because if you have a family, how to choose a good function? Does that make sense? So we need some condition to determine the c, because you remember, why, if suppose you have the graph of the function y like this, right? So what does mean y plus c? That means you need to shift the graph, right, up and down. Is that correct? So you have a family of this. So that means we need to determine just one, right, from this family. So you need some condition. That condition is called initial condition, right? Initial condition. So let's consider the following example. I have y equal to y prime equal to 3x plus 1. Okay, and y of 1 is equal to 1, for example. So this condition is initial, right? It means when x equal to 1, the y is also 1. We need to find the y. So I need to solve this integral 3x plus 1 dx, right? And then I can write y equal to integral of 3x plus 1 dx, and we use additivity of integration. I have this is 3 x dx plus just dx, right? And we know antiderivative of x is x squared of 2, and antiderivative of 1 is just x, and don't forget the constant c here. So that is our family of antiderivatives. And of course, from this family we need to determine only one curve satisfying this initial condition. So I write when x equal to 1, we have y1 is 3 over 2 times 1 squared plus 1 plus c. And from the initial condition, that is just 1. And this equation helps us to solve for the c, right? So from here I get c equal to negative 3 over 2. Negative 3 over 2. Because you cancel 1, right? And then this term, you bring to another side, so you change the sign, you get negative 3 over 2. And then you plug this back here, and you find your function, that is 3 over 2x squared plus x minus 3 over 2. And only this curve satisfies the initial condition right here. Does that make sense? So that means if you change the initial condition, you would have another curve, you will have another antiderivative. Don't forget that. Let's consider the following example. Let's find the general solution of the following differential equation: f prime x equal to 1 over x squared when x is bigger than 0. Okay, and find the particular solution satisfying the initial condition f1 equal to 0. Alright, so first we need to find general solution. That means we just need to integrate this function, the function 1 over x squared. So from here I can write f of x equal to antiderivative of dx over x squared. And we know how to integrate such function. We write that in the power function line x to negative 2 dx. And then we use the power rule, x to negative 2 plus 1 over negative 2 plus 1 plus constant. So that is, you have x to negative 1 divided by negative 1 plus c, or you write negative 1 over x plus c. So that's your general solution. Okay, general solution involve constants in here, and a particular solution for the function that f1 equal to 0. That means you have to plug 1 into this function and you set this equal to 0. Okay, from here I get negative 1 over 1 plus c equal to 0. Then your c is just 1. So the particular solution is fx equal to negative 1x plus 1. That's it. That's how we can solve differential equations with an initial condition. So basically you need to find antiderivative, right? You need to find general solution, and then in order to determine the c, you need to use the initial condition. Agree? Look at this. This is pretty simple because you know the derivative, right? And you need to recover the function with some initial condition. Basically it says, yeah, velocity, and you need to find the function of the distance, right? Okay, now let's say they give you acceleration. That means the second derivative. Okay, like we know f2 prime equal to, I can pick x for example. Okay, we need to find f of x. So how do you think? Can we use the same method? First we integrate that, right? You get the first derivative, and then you integrate that one more time, you get the function. Agree? So firstly let's find the first derivative of this. I have the first derivative is antiderivative of the second derivative. So that is antiderivative of x dx. And that is x squared over 2 plus constant. Let me write c1. So you see, if you know the second derivative, you can recover the first derivative, right? But in that case, we have one constant. Now, if you want to recover from the function from the first derivative, you integrate one more time. Is that correct? So let's find f2 prime. F just f of x, sorry. F of x. We see that f of x is antiderivative of f derivative, right? So I just plug x squared over 2 plus c1 dx in here, and then that is 1 over 2 antiderivative of x squared dx plus c1 dx, because c1 and 1/2 are constants, so we can take them out of the integral, right? Then we have 1/2 in here. We have x cubed over 3 plus c1 times x plus C2. We have two different constants in here. Does that make sense? So let's simplify that. In general, you have x equal to 1/6 x cubed plus C1x plus C2. So your general solution depends on two constants, right? That means in order to determine the function, you need at least two conditions. Does that make sense? So we can write here, all right? We need two conditions to determine the function, because we need to determine C1 and C2. We have two variables, C1 and C2. So we need at least two conditions. So one condition is for the function, and another condition is for the first derivative. Does that make sense? So you see, in this situation, yeah, we need two initial conditions, but one is about, for example, x0 equal to y0. That is for the function. And the second condition is f derivative at x0 equal to some okay, let's say z0. Okay, so if you have these two conditions, you may solve for C1 and C2. Agree? Suppose that, let's continue this problem, right? And suppose that f at x0 at 0 equal to, let's say, 1, and f derivative at 0 is equal to, let's say, 1. So that means the coordinate, right? The initial position of the function is of that object is 1 when the time equal to 0, and the initial velocity, you see this? This is the initial velocity, right? If we look at this from point of view of application. So that is the initial position. Okay, now I will plug these two conditions, right, into the equation of the function. So I get the following one. When x equal to 0, the function is 1, so C2 is just equal to 1. You see that? And then if you want to use the condition for the derivative, you need to plug x0 into this. This f derivative at 0 is 1, right? So you plug 0 into this guy, you get f derivative at 0 is 1. From here you can solve for C1. This is also 1. So you plug C1 and C2 into this formula, you get the particular solution with these two initial conditions. That is 1/6 x cubed plus x plus 1. You see, of course, if they give you the third derivative and they ask you to recover the function, right? So probably they need to give you three initial conditions. The first initial condition for the function, and then the second is for the derivative, and the last is for the second derivative. Agree? In order to finish this video, let's solve the following problem with the vertical motion. We suppose that a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. You see, you already have two initial conditions in here, right? The initial velocity and the initial height. Okay, assume that the acceleration is 80 equal to negative 32 feet per second squared, means per second, and they ask us to find the position function given the height s as a function of the time t, and when the ball, they ask us when the ball hits, the graph. Okay, so if you graph, if you describe this motion, you will see the following picture. So here's the height, the initial height. The initial height is 80, right? So you have 80 in here. This is for t equal to 0. You have s 0 is 80. So you have some height in here, okay? And then this is your, t, that is your s. And at this moment, s derivative means the velocity is 64. Okay, I just write 64. And then you give some initial velocity, right? You get this, velocity. So your object will fly like this, attain, the maximum height in here, and then go down. And that will hit the ground right here. And of course they ask us to find this. Ask us to find this, that means you just the x-intercept, right? That's just the x-intercept. There's nothing special. Does that make sense? Because when the ball hits the ground, so the height is just 0. That means you need to find the x-intercept. In this case, we might say, yeah, the t-intercept. Agree? So they gave us acceleration, you see? That means the second derivative. And they asked us to find the function, the position function, with some initial conditions in here. Agree? So it means we need to use integration. That's it. So I need to integrate the acceleration to get the velocity. I have velocity is equal to antiderivative of 32 dt. So that is negative 32, right? And then dt, you have negative 32t plus constant in here. And in order to determine the constant, I may solve like previous example. I might find the st with constant c1, c2, right? And then at the end I will use initial condition. But let's solve that. Let's find constant in each step. Okay, so that is s prime t equal to negative 32t plus c, and from the initial condition when t equal to 0 I get 64. That means this is equal to negative 32 times 0 plus c. So c in this case equal to 64. Then I plug 64 back here. I get s derivative t equal to negative 32t plus 64. And now I will find the height function, right? st equal to integral of s prime t dt. That is integral of negative 32t plus 64 dt. And you get negative 32 t dt plus 64 dt. Okay, antiderivative of t is t squared over 2 times negative 32 plus 64t, and then plus constant in here. So you have st equal to this. You might simplify. Okay, so let's try. Let's try negative 16t squared plus 64t plus c. So this is a parabola. You see, it's a parabola. Okay, so in order to find this c, I need to use the initial condition for this function. I mean the initial height, which is equal to 80. So I plug t equal to 0 into this expression. I get s0 equal to c, right? Because all the terms are 0. So this is equal to 80. From here I get, st is negative 16t squared plus 64t plus 80. And that is the position function. Okay, so we finished with the first question. The second question they ask us when the ball hits the ground. So the ball hits the ground when st equal to 0. when the height is 0. So I just put negative x 16t squared plus 64t plus 80 equal to 0, and I solve for the t. Is that correct? And we have quadratic formula, but before that I want to simplify a little bit, because I see 16 here, 64 and 80, right? So we might simplify by 16. So I have negative t squaring here, and then here plus 4t, and here I have 5 equal to 0. Yes, in this case I think we are lucky because we don't need to use quadratic formula. But anyway, let me write it down. I have t12 equal to plus negative b plus minus square root of b squared minus 4ac over 2a, right? In case. But in this situation, we have very special form. In this case, we have a minus b plus c equal to 0. Where, a is negative 1, you see, b is 4, and c is 5, you see. Coefficient satisfies this condition. In that situation, t equal to negative 1 is a 0. I hope you know this. In this case, t equal to negative 1 is a 0. So I may factor this function by t plus 1. Does that make sense? So I can write negative t squared plus 4t plus 5 equal to t plus 1. And we need to do some division, but in this case, the situation is simple. So I have t in here, I have negative t squared in here. That means in this term, I would need negative t, right? For free coefficient, I have 1, here I have 5. So I need plus 5. Does that make sense? And then you set this equal to 0. From here you get t equal to negative 1 and all t negative t plus 5 equal to 0. That means t equal to 5. So, of course, your function has 2 intercepts. This function has 2 intercepts, but only one intercept is positive. You see this? There's only one point here. Of course, another point is right here, right? You have negative 1. You see this? But since t is the time, so you only consider positive value. So the ball will hit the ground after 5 seconds. And that is the answer for the second question. So I think I will finish my video in here, and I hope that we have enough examples that shows you how we can apply integration in real world problems. Okay, and again, solving such problem or integrating means we recover the function knowing its derivatives. So whatever they give you, the first or the second or the third, right? And if they want you to determine a concrete function, they should give you some initial conditions. That's it. Agree? Just step by step, and then we can solve the problem. Alright, so if you have any questions, please feel free to let me know. I finish my video in here, and see you in the next video.